Hi, in this video I will explain the different factors that affect the physical properties of alcohols and alkyl halides. And we will start with the boiling point. So the physical properties of alcohols and alkyl halides and all other organic compounds are affected by the type of intermolecular forces that exist between the molecules of these compounds. There are three types of attractive van der Waals forces which may exist in organic molecules, and these are dipole-dipole interactions, dipole-induced dipole interactions, and induced dipole interactions. Usually the first type, which is a dipole-dipole interactions, it exists mainly if we have polar compounds. So if you have two polar compounds, then the type of interaction between them will be dipole-dipole. The second one exists between polar compounds and non-polar compounds. And the last one, it exists in all molecules, but it's only important if we have non-polar compounds. So all types of molecules will have London dispersion forces. However, London dispersion forces or induced dipole interactions are only important if we have a non-polar compound. This picture shows us what does a dipole-dipole interaction mean. So first of all, here this is a dipole, which means that we have a polar bond. We have positive and negative regions, and then this is another molecule which has also a positive and negative region, and then there will be an interaction or attraction between the negative or the high electron density region here and the low electron density region here, and this is how molecules get attracted to each other. If you look at the boiling point of the different types of organic compounds, so this is an alkane. The boiling point of this alkane is minus 42 degrees. If you have a fluoroethane, so it has they almost have the same molecular weight, and now the boiling point is negative 32 degrees. And finally ethanol, the boiling point is 78 degrees. So we will explain why do we have such a high boiling point for alcohols, whereas we have a low boiling point for this alkyl halide and even a lower boiling point for this alkane. So let's look at the main factors which affect the boiling point of alcohols and alkyl halides. And it's basically the functional group which plays the major role in determining the physical properties and the strengths of these physical properties. So alcohols are characterized by the presence of the hydroxyl functional group or the OH group. This OH group leads to the formation of a polar OH bond and a polar CO bond. So in alcohols in general, we have two polar bonds. We have the oxygen hydrogen bond, this is one polar bond, and then we have the carbon oxygen bond, which is another polar bond. So we have two polar bonds in alcohols. And since alcohols are polar molecules, that's why dipole-dipole interactions will exist between two alcohol molecules. So if I have methanol and another methanol molecule, the main type of interaction between these two molecules will be the dipole-dipole interaction. This number, which is here, it tells us basically the magnitude or the strength of the dipole moment. So it tells you how polar is the compound. It's 1.7 dpi for methanol. And the electrostatic potential map also proves and gives more information about the polarity of methanol. So as you can see here, this red region indicates that we have high electron density around the oxygen, and then this blue region indicates that we have low electron density around the hydrogen, and this is again because this is a polar bond, so hydrogen is partially positive, oxygen is partially negative, and this is almost a green region. So although oxygen is withdrawing electrons from carbon, but the electron density decrease is not as in the case of hydrogens, which are here. So anyways, to summarize, this proves that alcohols are polar molecules. Let's talk about alkyl halides now. Alkyl halides have the functional group, which is the halogen. And of course, if the halogen is more polar than is more electronegative than carbon, then we will have a more polar carbon halogen bond, and again dipole interactions exist. For example, in this case here, so this is chloromethane. The carbon chlorine bond is a polar bond because chlorine is more electronegative than carbon. That's why carbon will be partially positive and chlorine will be partially negative. And again, if you look at the magnitude or the strength of the dipole moment, you can see that it's equal to 1.9 dBis, which is even more polar than methanol. So chloromethane, for example, is a compound which is more polar than methanol. And this is again the electrostatic potential map, which shows us that we have a red region around the chlorine atom, and this is because of the high electronegativity, which is pushing the electrons to go to chlorine. And then we have a blue region here at the carbon, and this is because of the low electronegativity of carbon. So most of the electrons are shifted toward the chlorine side. Now, surprisingly, if you look at the boiling points of alcohols and chloromethane, you can see that alcohols have a very high boiling point compared to chloromethane. So although chloromethane is more polar than methanol, it has a very high boiling point compared to that of alkyl chloride. So why is that? So it's basically, what it's just telling us is that bond polarity or molecular polarity is not the only factor. So it is one factor, but there is another factor. So it's not the only factor which affects the boiling point. So what is the main factor which is leading to this result? What is the main factor which makes alcohols have higher boiling points than alkyl halides? Alcohols, this is the main reason, is that alcohols can make hydrogen bonding. What is hydrogen bonding? It is a special type of dipole-dipole interaction. So dipole-dipole interaction is one type of intermolecular forces. And an example of dipole-dipole interaction, or one type of dipole-dipole interactions, is hydrogen bonding. And hydrogen bonding exists only if there is a hydrogen atom bonded to a highly electronegative element such as oxygen or nitrogen. So you can only have hydrogen bonds if you have a hydrogen bonded to an oxygen, or if you have a hydrogen bonded to a nitrogen. In this case, your compound can make hydrogen bonds. Otherwise, no. And the hydrogen bonding, it occurs mainly between the hydrogen atom and the lone pairs of the other elements. So let's say we have one compound which is an alcohol which has ROH group. Hydrogen bonding will be between the hydrogen of one alcohol and the oxygen of another alcohol. This is hydrogen bonding. So it exists between two molecules. The first molecule will be donating its hydrogen, and the second molecule will be donating or using its lone pair. This is hydrogen bonding. This interaction, which is keeping this partially positive hydrogen and partially negative oxygen together, is called hydrogen bonding. And it keeps those two molecules very close to each other. The hydrogen atom is called the hydrogen bond donor. So, and the oxygen or the element which is giving its lone pair is called the hydrogen bond acceptor. So this molecule here is acting as a hydrogen bond donor. It's donating our hydrogen, and this one is accepting the hydrogen bond since it's using its lone pair. For example, in this case, this is an alcohol molecule, and this is an amine molecule. And as you can see here, in case of alcohols, as I said before, the hydrogen, which is partially positive, will be attracted to the oxygen of another alcohol, which is partially negative. Because of these opposite charges, those two elements will be bonded or interacting together. They will be attracted together, and this is called hydrogen bonding. Again, in the case of amines, one molecule of amine will be donating its hydrogen, and the other amine molecule will be using its lone pair, and this is hydrogen bonding. So this is how hydrogen bonding is formed in molecules which are capable of forming hydrogen bond, and this is the main reason which makes the boiling point of alcohols or amines very high compared to other compounds. So hydrogen bonding is a strong type of interaction, and because it's strongly attracting molecules together, the amount of energy which is needed to break the bonds between molecules will be higher, and that's why the boiling point will be higher. This figure here shows us how many different hydrogen bonds can let's say 2 or 3 molecules more. So you can see that they are going to be a network of hydrogen bonds. So for example, this is one ethanol molecule, this is another methanol molecule, and then this is a third ethanol molecule. So this is one hydrogen bond which exists between the first molecule, molecule 1, and molecule 2. However, since we have 2 lone pairs at oxygen, you can see that oxygen here, this compound here, which is acting as a hydrogen bond donor, so it's donating its hydrogen, can also act as a hydrogen bond and acceptor, and it can form an interaction with another molecule. So each alcohol molecule can act as a hydrogen bond donor by donating its hydrogen, and also as a hydrogen bond acceptor by accepting a hydrogen bond from another molecule. Again, this molecule, which is here molecule 2, which is in this case acting as a hydrogen bond acceptor, can also act as a hydrogen bond donor and can donate its hydrogen to interact with another ethanol molecule. So anyways, you can see here that there will be a network of hydrogen bonds between the different alcohol molecules. Because of this network, the boiling point of alcohols will be very high, because you need energy to break all these interactions and then separate the molecules and move them from the liquid state to the gas state, and that's why the boiling points will be high. So what are the factors which affect the boiling point of alcohols? The first factor which should be taken in consideration is the number of carbons or the molecular weight. The boiling point of alcohols increases as the number of carbons increase. So whenever you are given a number of alcohols and you are supposed to arrange them according to their boiling point, the first thing you should be doing is finding the total number of carbons in the alcohol. And as the number of carbons increases, the boiling point increases. Why is that? Because increasing the number of carbons will increase the surface area of the molecule. So the molecule will be larger in size. And when the molecule gets larger in size, then the interaction between the molecules will be higher. So look at these molecules. We have 2 carbon here. So this is C2, this is C3, and this is C4. And as you can see here, as the number of carbons increases, the molecule is getting larger and larger in size. And because of this larger size, the interaction between this molecule and another similar molecule, so this surface area of interaction will be higher. And since we have a higher surface area of interaction, that's why those molecules will be closely held and attracted to each other. And again, this is why their boiling points will be high, because you have too much interaction, you need too much energy to separate them, and that's why the boiling point will be high. As you can see here, these are the boiling points of the different alcohols. So one carbon, 65, 78, 2 carbon, 3 carbon, 97. So as you can see here, as we increase one carbon, the boiling point is increasing. The second factor which should be taken in consideration also is the number of branches. For compounds that have the same number of carbons, you should look at the branches. And as branching decreases, boiling point increases. So the alcohol which has more branches will have a lower boiling point. And the reason is that branching will decrease the surface area of the molecule. So all these compounds have 4 carbons. However, as you can see here, this one has 2 branches, which are this one and this one. This one has only 1 branch, and this alcohol has no branches. And as you can see, as the number of branches increases, the surface area of the molecule decreases. So we have a smaller size molecule. Because of this smaller size, the interaction again with other molecules will be smaller, and because of this, the boiling point will be lower. So the second factor which should be taken in consideration is the number of branches. As branching increases, boiling point decreases.